that means that mine is like basically a dinosaur. It's just like ancient.
All right. Any questions?
How's your day?
What?
How's your day?
My day's good, thanks.
You're welcome.
I just had a bag of potato chips.
What
lunch.
flavor?
Yeah.
What flavor?
Plain.
Plain?
Yeah. Classic.
What brand?
Lay's.
Okay. That's the best kind you can get out of the menu.
Yeah, that's something I haven't had in like months. Good thing.
Salty movie potato chips?
Yeah. All right. Other questions?
What is bubblesort?
I understand that.
We're going to talk bubblesort. That's our second main topic today. All right. Any questions on the ODP?
From yesterday? Tonight?
Yeah. No, the one that was already turned in today. We don't have a new one.
Well, I have to get it out anyway. I'm taking notes on it.
It's not that different, right? From last
Nope.
night, right? So why is it important to like include the index? Wouldn't it just like leave it in an indefinite amount if we didn't?
Well, where would you store it if you didn't give it the index? Right. So you're talking about the put function.
Yeah.
So put, you're giving it something to save, but you also have to tell it where to save it.
I see.
Right? And then you use that in the global array to actually store it.
I see.
Question.
Yes.
So I need an array for my global variable.
Good.
Is that what we're supposed to do?
That's what you're supposed to do.
Okay, good.
Yeah.
Global. Yeah.
Yeah, so I called mine save value, but it's just an array of 10 integers and it's declared outside the function, so it's global.
Oh, I get it. It's an array of 10 integers. And if it
Yeah.
wasn't an array, it would just say 1.
It would just save 1, yeah.
I see.
And if it wasn't an array and I tried to do this kind of thing, I'd get all kinds of weird compile messages and maybe seg faults. And it ran. All right, so we were playing around with standard in and standard out and standard error, and this idea of redirection. So normally when you run a command, if it tries to read from standard in, like with an fgets or a getcar, it reads from your keyboard. And if you run a command and you say less than the name of a file, then it reads from that file when you try to read from standard in. And if something is trying to write to standard out with a printf, normally it appears on your screen. If you say command greater than file, it goes into that file instead of appearing on your screen. And if you do two greater than signs, it appends to the file. A single greater than will just overwrite the file. And I think we ended yesterday by saying if you do a greater than ampersand, it also redirects this other stream called standard error.
Would you be able to do the append syntax and then ampersand to append an error file?
I think greater than ampersand will do that. So this should give me lots of errors. So it wouldn't give me that many errors. This should give me lots of errors. I wanted it to give me lots of errors. Okay, let's do this. Okay, there's lots of errors. So let's take the date and put it into a file. And then let's do our GCC. And let's do greater than at file. Doesn't like that. I don't know how to do that. So if I just do greater at file, it'll go into file, but it overwrites from the beginning. I don't know. I don't know if you can append standard out. Google it. Let me know. There's probably a way. That's definitely not going to do it. Interesting. All right, yeah, there's probably a way. All right, so we can redirect standard out, standard in, standard error. This is actually standard error and standard out. All right, so we also have this business of piping. So we can say command 1 and pipe that into command 2. So here's an example of piping. I can say ls-l/bin, and I get a whole bunch of lines of output, and I want to know how many files there are. If I could feed this to the word count utility, wc, that counts how many lines of input it finds. So here's something I could do. I could do ls-l/bin and send the output into a temporary file, and then I could say word count on that temporary file, and I get 168. So I know there's 168 lines that were output by ls-l. And you can do the same thing without having a temporary file by using a pipe. So I can do ls-l/bin and then pipe that into word count. And that says take standard out from this command and connect it to standard in of that command. So it's like taking this, sending it to a file, and then feeding that file into word count. Yes?
Is that bash 4?
You mean version 4?
Yeah.
I don't know what the difference is with different
Try
versions.
an ampersand before the greater than.
Oh, amper greater. Hey, there we go. So there's my ls, there's that. Okay, cool. Thank you. So you can append, and you can do ampersand greater to append standard error. Was that Google?
Yeah.
Cool.
Stack Overflow.
Yeah, awesome. All right, thanks. All right, so this pipe basically says take standard out of this command and connect it through, you know, like a water pipe to standard in of that command. And we can chain these things together. We could take the output of command 2 and we could pipe that into another command 3. And we could take the output of that and we could say append that to a file. And you can chain these things together however your brain imagines it. And we'll see good reasons for doing this in the coming weeks as we dig more into bash. So this pipe connects standard out to standard in, and you can also do cmd1 pipe ampersand cmd2, and that takes both standard out and standard error and sends those to standard in of command 2. And one way that that's immediately useful, we have this business of compiling a program that generates a bunch of error messages, right? And we can put that into a file and then VI the file and so on, but that's a bit of a pain. Remember, we have this program called more, right? We can say more and feed it input from a file, like temp, and it will show us the contents of that file one line at a time. I mean, one page at a time. And we can go forward pages by hitting the space bar. We can go forward a line by just hitting an enter key. So if I say gcc haha.c and I pipe that into more, right, the goal is to take all those error messages that GCC produces and be able to look at them one line at a time. And this doesn't exactly work because those error messages aren't going to standard out, they're going to standard error. But if I do this, and I say also redirect standard error, now I compile my program. If there's any errors, I see them, and it's just the first page of errors I'm looking at. First error is at the top of the page. And then if I want to see more errors, I can just space forward with the space bar, go through a page at a time until I get to the end.
And so that.
Good.
So why do errors get treated so special compared to standard?
So when you run a program and it's generating output, right? Usually you write the standard out with a printf and so on. You want to save that output to a file. Suppose you're redirecting your output to a file, but you really want the user who's running the program to see something on their screen, right? Like you know, the system is running out of power. We're about to shut down. Save your work, right? You don't want that message to get redirected into the file, right? So that's something you could put out on standard error. And usually when you redirect output, you just use a greater than or a pipe. So that's stuff on standard out goes wherever you tell it to go. But then you still have standard error to print out things that are unusual, typically error messages, which is why it's called standard error. All right, do you have a question, comment?
Oh yeah. So if you just wanted to redirect the error, would you just do and?
I don't know if there's a way to do that. No, I don't think an and will do it, because an and is how we throw things in the background. It seems to be standard out or standard out plus standard error. But you could cobble together some really quirky strings where you put it into a T and take one stream and redirect standard out and another and direct both and then do a difference maybe. And you could do all kinds of interesting things like that. Alright, so these pipes are useful for different things. Alright, so there's classic examples. If I do who, it shows me everybody who's logged into the system. If I do who pipe into word count, I know there's 15 people logged into the system.
Nice.
And so on. All right, so the other thing I want to talk about is backquotes. So we know what double quotes are, because they look different. We do single quotes, and they're usually drawn as just a little up and down notch. But on the keyboard, they're actually a forward quote, kind of like a forward slash. They go from upper right to lower left. There's also a back quote. And a back quote on my keyboard, it's in the upper left corner of my keyboard. It's next to the tilde button. It shares with the tilde button. And it's next to the exclamation mark. And back quotes are different. So I can echo double quote date. It's going to say date. I can echo single quote date, and it still says date. If I echo back quote date, actually echoes the date.
If you use a to and then the redirect, the greater than, then it's only.
Oh, it's only standard out. Okay, makes sense because standard error is stream 2.
Yeah.
Cool. 2 greater than?
Mm-hmm.
Okay, awesome. Thank you. All right, so what's happening when we say echo back quote date? Here's what bash does. It looks at the thing inside the back quotes. It assumes this is a command. It executes that command. It captures standard out, and then all of this gets replaced with whatever was sent to standard out by that command. So if my command is date, it runs the date command. It gets that string, you know, Wednesday, blah, 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 and it replaces this backquote date backquote with that output, and so now my command is just echo that thing that looks like the date. And if I say echo backquote pwd, same thing. And if I say echo ps pipe into word count, right, it runs the ps command, which shows me all my processes that I have running. It throws that into the word count utility. Word count outputs 5 lines, 20 words, 140 characters. That's what it echoes.
I know that we're using echo as an example, but
Mhm.
why not just type in date?
Because we can do this, x equals backquote date. Now I've got a variable named x whose contents is the date.
Needs.
Yeah.
So, if you use date or time or something that
Mhm.
changes every millisecond or second,
Mm-hmm.
and you put x is equal to that, and then echoed the x, would it just be what the date was at the time that x was?
Yeah, so if I echo x again, it's exactly the same value. It's really just a variable. But it got its value by running the date command at line, 2024.
This is backquote only work in bash.
There's other shells that do it or do something similar, but
So
yeah,
it's
this
not
is
like a C
pretty,
thing.
no, this is pretty bash specific.
Cool.
C wishes it had something like this.
I agree.
It's too low.
Yeah, but this is power, right? And in some sense, this is like the past 34 years of my life has been spent with backquotes. That's where cell matrix came from, basically.
Is this almost like calling functions? Like you could like
Yeah,
needs.
right. So what's DATE? Is it a piece of data, a word containing 4 letters, or is it a piece of code that runs a function that shows you what the current date and time is?
And
Right.
does that allow you to also
redo
use,
PA1 doing this.
does that also allow you to use variables?
Yeah.
of the backquote.
So x equals date, right? X is just the word DATE, but I could say y equals backquote $x, and now y is equal to the date. But if I said x equal to pwd, and I say y equals backquote $x, now y is my current directory.
So it's string concatenation with extra with
Mhm.
less steps.
Yeah.
So could you write your own custom functions like a bash script and then have it return actual values?
Yes, exactly. So this is one thing that makes backquotes really useful in bash. So let's make our square function. So here's a little bash script called square. You give it an argument on the command line and it prints out the square of that. Right? Let's say we wanted to use that in another script. I'm pushing my luck here because I haven't tried this.
I don't think that's gonna work. I know in JavaScript, it's got the same thing. It won't do it because the double quotes are like the top.
The double quotes won't kill the back quotes, I'm pretty sure of that. Let's see if it works. If it doesn't, I'll make up an excuse for why it doesn't work. Alright, stuff, enter a number 7. The square of 7 is 49. So what's going on here, right? We prompt, we get a number n. This says execute the command square with the value that we typed in, 7, right? And square 7, square is a script that just takes a command line argument $1, squares it, and prints that out. But it didn't print it out because it's inside back quotes. That section that's blocked off right there gets replaced with the output of the square script, which is the number 49, and so it echoes the square of 7 is 49. So we can sort of capture return values from functions using this. In fact, we could print out anything that we wanted and grab it and store it right here. And more generally, x equals backquote square 17. So x is equal to the string 289. But we could print out multiple things and capture all of those and then break them apart and so on. So that's one use for backquotes. It's a way to link functions together. All right, so you want to mess around with these, right? Play around with them, and another week probably we're going to start talking about more bash functions, sed and awk in particular, and we'll see lots of uses for doing these kinds of backquotes and stuff. So this will be useful. All right, ready to talk bubble sorts?
You say bubblesort?
Bubble sort. Like bubble tea.
Bubble tea.
All right, so PA4, one of the requirements at the end, you've got your dictionary of phrases. You're supposed to output those in increasing phrase length, right? So your shortest phrases appear first, your longest phrases appear at the end. So you have to do some kind of sort on your dictionary to order it by phrase length. And I suggested in the assignment use a bubble sort. Okay, so first of all, there's a bunch of different ways to sort data. Sorting is a really old problem, right? More than half a century. People have been sorting data using computers or algorithms. And in 222, we'll spend at least a week, probably 2 weeks, just talking about sorts. And we'll learn about bubble sorts and selection sort, insertion sort, tree sort, heap sort, quick sort, all these other kinds of sorts, radix sorts, sorts of sorts. And there's no one sort that's the best for all situations. There's some sorts that work really, really, really well unless your data is almost sorted to begin with. And then they just have horrible performance. And there's some sorts that work really well on small amounts of data but are terrible on large amounts of data. There's some sorts that work really well if your data has certain characteristics to it but falls apart with other kinds of data. So there's no one, best sort, but there are possibly some worst sorts. And in some sense, bubble sort might be one of the worst sorts overall. But it's probably the only sort I've ever actually used myself, other than in a classroom, right? So when I took data structures, I had to code up quick sorts and all of this stuff. But when I have to write a sort routine, I always write a bubble sort. Why? Because it's probably the easiest sort to write out of all the possible ones. Right, and Unix we have a sort routine, a sort function that you can just feed an input and it'll sort the output for you, and you can feed it a set of numbers and sort -n will sort them in numeric order. I think that's where my input ended and the sorted output. So there's usually sorts available, and there's sorts available in C and so on and so forth. But if you have to write your own, bubble sort is a pretty good go-to. And the idea of bubble sort, let's make a set of data. All right, we'll sort 8 things. So you have n pieces of data. So think of maybe an integer array of size n. Here's the sort of physical idea behind bubble sort, right? Picture rocks in water, and the rocks are heavy and they sink down to the bottom, and bubbles are light and the bubbles float up to the top. Okay? That's kind of what happens with a bubble sort, is that we make a series of what we call passes through our data, and each pass, the next heaviest thing that should be at the bottom of this array of data sinks down to the bottom. So our first pass, the goal is to find the largest number in here and move it into the bottom position. So after our first pass, the 9 should be sitting down here. Who knows what's in the rest of the spots here? We're only worried about adjusting that last position. The second pass of all the remaining numbers up here, the largest one should sink down into the second position. So that should end up with an 8. And the way bubble sort is done is by comparing each element in the array to the number after it, and seeing if relative to each other they're in the correct position. So for example, we start off, this is one pass. We look at 4 and 2. Those are in the wrong order, right? 2 is smaller than 4, so that should get swapped. This should be a 2, this should be a 4. 9, 6, 3, 5, 8, 7. Okay, so we started with that. We did this swap. Now we look at 4, and 4 and 9 are in the correct order. We look at 9. 9 and 6 are in the wrong order, so they should get swapped. So this one we swapped 4 and 2. So we swapped 9 and 6, so now our array looks like this. And now we look at 9, and it's in the wrong order relative to 3, so those should get swapped. And we look at this one, and 9 and 5 are in the wrong order. And you can see what's happening. We already found the biggest number in the array, and it's swapping spots with everything below it because it's the biggest number. So now we check this element, and that's out of order with 8. And finally we check this last element. 9 and 7 are out of order, so we swap them. And so that's what the array looks like after one pass. Well, that one pass has done the following for us. It's guaranteed that this is where the 9 belongs. We had no idea about anything above it. So now we make a second pass. So we start with 2, 4, 6, 3, 5, 8, 7, 9. We look at this, the order's fine. We look at this, they're in the wrong order. So we need to swap them. I missed a number. 2, 4, 6. Alright, so 2 was in the right spot, 4 was in the right spot, 6 and 3 needed to swap. So 2, 4, 3, 6, 5, 8, 7, 9. We look at the 6, it's out of order. We look at the 8, that's out of order with the 7. And we look at the 8 and the 9, and they're in the correct order. And so that's the second pass, and after the second pass, we've got 2 things in the right spot.
You have to manually pass it, like, each time?
What do you mean?
I'm sorry, just go ahead.
Okay.
Yeah.
Alright, so each time we make a pass, another piece of data moves into the right spot. We have a total of n pieces of data that we want to sort. So we have n pieces of data that we want to end up in the right spot. So if we make n passes, we should certainly end up with our whole array sorted. We can actually do n minus 1, because once this number and all other numbers below it are in the right spot, we know the first number is in the right place too. But we're not going to worry about details, right? So we're going to do n passes. And each pass we want to move the largest thing into the bottom. Okay, so let's code this. So we'll have an integer array of data, and we'll have an n, which tells us how many pieces of data do we have. So let's look at this inner pass first. So this inner pass, we want to take each number and compare it to the number after it. And if they're out of order, we want to swap them. So our inner pass, we're going to compare data bracket I with data I plus 1. Or we compare data I minus 1 with data I if we started at 1. Either way, let's do that. We'll do it differently from how I did it last time. So let's compare data I minus 1 with data I. So my index I is going to start here, and it's going to go down to there. And wherever I is pointing, we're going to compare the thing before it with the thing at I. And we're going to swap them if they're out of order.
Why not do
You could do a while. You can always do a while instead of a for. You can kind of always do a for instead of a while.
Okay.
But we know how many times we want to do this, right? So for loops kind of come to mind when you have a starting and ending point in mind that correspond to numbers, basically. I want to start with the first element and I want to end with the n minus first element. Or I want to start with the second element and end with the last element, the nth element, right? When you have sort of a starting and ending value, that kind of brings a for loop to mind.
Okay.
When you have a condition that you want to end on, like when there's no more input or when this is greater than that, that's kind of where I would do a while loop.
Okay.
But it's personal taste. So here we're going to go I equals 1, I less than n, I plus plus. So what do we want to do? See if elements I minus 1 and I are out of order. Okay, so they're out of order if data bracket I minus 1 is bigger than data bracket I. So if the number before I is bigger than the number at I, those are in the wrong order. And what do we want to do? We want to swap these. And that's pretty much the whole inner loop. Just march through all the data elements, and for each one, see if it's in the wrong order relative to the next one, and if it is, swap them. And that gives us one pass through our data. And we want to do that whole thing a number of times. So this is the end of the inner pass. This is the end of the outer pass. And this is the end of the swap of two elements. We still have to write that code. Okay, why is this going to work? Because make one pass, get the largest thing in the bottom. Make a second pass, we got two things in the bottom. Make a third pass, we got three things in the correct spot. After n passes, we should have n numbers in the correct position. And since we only have n numbers, everything should be sorted. And how do we know that this inner pass actually does what we claim it does, puts the largest thing at the bottom? Well, it kind of has to, right? Suppose that we finish our inner pass and there was a 10 sitting somewhere in here that was not at the bottom. Maybe there was a 10 sitting up here. Well, if that 10 is bigger than every number in the array, then it should have gotten swapped with the number after it, because it would be bigger. And then when we compared it to the number after that, it should have gotten swapped again because it's the biggest number in the array. And when it's down here, whatever the next number is, it's got to be bigger than that because it's the biggest number in the array. So we keep getting swapped until it ends up down at the bottom. Now in algorithms course, you'd like formally prove that this actually works. And that takes a little more hand waving. But that's the idea of it, right? So this should be a nice bubble sort. So how do we swap this stuff in the middle? So imagine you have, A equals 10 and B equals 20. And we want to swap these around so that at the end A is equal to 20 and B is equal to 10. Right? So this is something that comes up periodically in programming. So this part's easy. That'll set A equal to 20. And we could try to do this. But that's not going to do anything because this is going to set A equal to 20 and this is going to set B equal to 20 because A is 20. So both of these will end up being 20 instead of A being 20 and B being 10. So how do we deal with this? Make a temporary variable. So let's make a variable called save A and set that equal to A. So save A is equal to 10. Now we can set A equal to 20 and then we can set B equal to that saved value of A. So that'll swap them. And that first time I encountered this, it really tripped my brain out for I don't know how long. It took a while to make peace with it. And the first, I don't know, few dozen times I tried to write it myself, it tripped my brain out. But eventually it makes sense.
You could also use subtraction.
Yeah, so you can actually swap two variables without actually using a temporary. And that's a fun challenge to try to do. Alright, so let's swap these. So temp equals data I minus 1. Data I minus 1 equals data I. Data I equals temp. And so that should be a pretty legit bubble swap, bubble sort.
So what's the difference between the inner pass and the outer pass? What happens between those two?
The outer pass just runs the inner pass, but it does it n times.
Oh, I see, and then the inner pass is the actual.
The inner pass is the actual go through and swap. Yeah. So the behavior of this function is to run that inner pass code n times.
I see. Okay.
And by the way, don't use k for your outer pass. I've told you this, but I know someone who lost points for that. Teacher took off points and said outer passes should use I, inner passes should use j. So I won't take off points for that, but if you do this for someone else, use I for your outer pass, j for your inner. But I did this one first, so it became I, and then probably k for a more inner.
Use ABC just to make sense.
Yeah, right. Or use each.
Why would you say that a bubble sort is the worst?
So let's talk about how efficiently bubble sort works. And here's a way to think about bubble sort. Okay, there's a rough outline of our bubble sort. For I equals 0, I less than n, I plus plus, do the following, which is for j equals 0, j less than n, j plus plus, do the following, which is some sort of stuff. It's an if statement and maybe some assignments and things like that, but something in here. So let's look at this inner stuff and say, how many times does this stuff happen in the course of executing this whole chunk of code? Well, let's break it down. Let's just look at this inner loop. J equals 0, j less than n, j plus plus. How many times do we do stuff?
N times.
Yeah, n times. Okay, forget about what happens in here. Just look at the outer loop. I equals 0, I less than n, I plus plus. How many times is my hand executed?
N.
Still n times, right? So we're doing my hand n times, and each time we do my hand, we have to do stuff n times. So stuff actually happens n squared times. This is sometimes called a back of the envelope calculation because we're pushing a lot of details aside, like the fact that we only go from 1 to n instead of 0 to n. But rough first order approximations basically do the stuff inside n squared times. And depending on the data, you know, this may just be a bunch of if statements that never get executed, or they may be if statements where we actually have to do 3 assignments. So it's really difficult for an arbitrary set of data to know exactly how many instructions are going to get executed, or to know exactly how many microseconds this algorithm might take. But roughly speaking, this inner part of our inner loop is going to get run about n squared times. Okay, so when we look at sorts or other algorithms, we're usually not asking how long will they take, because that depends on what the year is, right? If we run the same code in 1975, it's going to take a lot longer than in 2019. It depends on how it's written. If I write this in assembly language, it's going to run a lot faster than if I write it in MATLAB. And it depends on the particular data. If my data is perfectly sorted, if my data is completely sorted backwards, it's going to take different amounts of time. So we don't usually try to analyze algorithms in terms of how long do they take. We analyze algorithms in terms of how much worse do they get as our data increases in size. So suppose we have n pieces of data we want to sort, and we know it's going to take n squared operations. Okay, let's say we have 10 pieces of data in our array. We're going to do that inner loop roughly 100 times. We'll execute that thing of stuff in the middle. Suppose we double the amount of data. So n is 20. How many times are we going to do stuff? 400 times. Suppose we go up 10x on the amount of data. We go from 10 pieces of data to 100 pieces of data. How many times do we do stuff now? 10,000. Okay, so here's the idea. From here to here, our data increased by a factor of 2x. The time required increased by a factor of 4x. From here to here, the data increased by 10x. The amount of work we had to do increased by 100x. And so it feels like there's something quadratic going on, right? Doubling the data takes 4 times as much time. Tripling the amount of data would take 9 times as much time. So we say that this is order n squared. And we write it as a script O with an n squared in parentheses after it. And it's a measure for how efficient this algorithm is as the data gets larger and larger. And order n squared is pretty bad, because if you can sort 1,000 pieces of data in 1 second, 1,000,000 pieces of data is going to take you 1,000 seconds. Sorry, goes up by 1,000, it's going to take you 1,000,000 seconds. Right? Increase the amount of data by 1,000x, the time goes up by 1,000 squared x. So sorting 1,000 phrases, if it takes your program a second, that's not a big deal. But if you happen to have 1,000,000 phrases, it's going to take you 1,000,000 seconds, which is a really long time. And sorts that are n squared are kind of the worst performing sorts that people talk about. A better sort is something like order of n times log n. Because now if we increase by 1,000x from 1,000 pieces of data to 1,000,000, our time goes up by 1,000 times the log of 1,000. Well, that's about 10,000. So it's not linear. 1,000 pieces, 1,000 times more data takes more than 1,000 amount of time. It takes 10,000 the amount of time. But it's better than going from, 1 second to 1,000,000 seconds. So n log n is considered pretty good.
It's the best you can do in a comparison sort.
Yes. Well, on conventional hardware. This is a pretty nice ideal. Order n, basically the amount of time it takes is linear to the amount of data that you're working with. So increase the data 1000x, your computation time would go up by 1000x. That's usually something people can live with. Here's an even better system, order 1. So what does order 1 mean? It means you double the amount of data and it doesn't take any more time. Which means if you quadruple the amount of data, it doesn't take any more time, which means if you have 1 billion times as much data, it still doesn't take any more time than sorting 10 pieces of data. That's a really nice algorithm. And we'll talk about some algorithms that theoretically get order 1 performance. Hashes are one example of it. Here's my favorite though. Order 0. So order 0 takes no time to do your computation no matter how much data you have. That would be pretty cool.
Okay.
But it's not possible, right?
Well,
Like, even theoretically, it's not possible.
in my theories it is. Here's one you don't want. Order n to the n. Ooh, that's bad. And there's algorithms that the best we can do is something like order n to the n.
Why would anyone use that one specifically over any other one?
Because there's algorithms that we don't have a better solution for. And in fact, there's a whole class of problems whose solution, whose computational complexity looks like this as opposed to, say, order n squared or n cubed or even n to the 10,000th, right? And for some of these problems that have complexity like that, if you can find an algorithm that does polynomial time computation, even if it's a big polynomial like n to the 10 millionth, right? If you can find an algorithm that solves these problems in polynomial time, you can change the world with that. And you can also get $1 million from the Millennial Prizes for that. So look up traveling salesperson problem if you want to go down a little bit of a rabbit hole. It's good stuff. All right, so we'll start flowcharting some code for parts of PA4 tomorrow. We'll look at pulling out phrases. We'll do some flowcharting for that and dig into some details.
Just use a function nested inside of a for loop and call it like stage 2 or something, and just use I again.
Yeah, yeah.